Hey friends, Dr. Borole is here. Today we are studying the rectifiers. Those are used in AC to DC conversion. The rectifiers are called as AC to DC converter because they converts the AC main signal into corresponding DC signal. They are classified under two broad categories: half wave rectifiers and full wave rectifier, also called as FWR. Full wave rectifiers are further classified in two broad groups depending on the transformer used in these circuits. The full wave center tap rectifier, or it can be full wave bridge rectifier. The full wave center tap rectifier consists of a center tap transformer, whereas bridge rectifier use a transformer with a single winding. Most popular and commonly used rectifier in the electronic circuit is full wave bridge rectifier. So let's study first the positive half wave rectifier. The circuit diagram of positive half wave rectifier is shown here. It consists of a step down transformer. Since we need lower output voltage than the mains voltage is in Indian region 230 volt AC RMS 50 Hz single phase, whereas secondary voltage required is normally in the range of 5 volt to 15 volt, and therefore we need a transformer which can be a step down transformer. The step down transformer available in the market with the secondary and primary voltage rating, for example 230S to 12 volt, 230S to 15 volt RMS. In the circuit there is a single diode used, and RL is the load resistance. This load resistance may be the external circuitry which this rectifier feeds. RL represents the equivalent resistance of the circuit it is supplying the voltage or DC power. Let us consider the operation. During positive half cycle of the input, the secondary voltage also reproduce the same positive half cycle. If input is changing as Vm sin of omega t, then output secondary winding voltage is Vs sin of omega t, where Vs is the maximum voltage, peak voltage at the secondary output. Now during positive half cycle, we will see that at secondary, point A is more positive than point B. It makes the diode anode more positive with respect to cathode, and therefore diode goes in forward bias. When the diode goes in forward bias, it is ideally act as a closed switch, and therefore it connects the secondary voltage directly across the load, and the current flowing through this switch is denoted by IL here. The voltage across load during positive half cycle of the input is same as the positive half cycle again. Practically, you will see that diode is not a ideal switch, but it is a practical switch. Diode forward resistance is not ideally zero, but it is a low value resistance denoted by RF. Also, the transformer is not an ideal transformer. Its secondary winding has some resistance RS. This resistance RS is in the range of few ohm or fraction of ohm for high power transformer. Similarly, RF is also few ohm. So total RS plus RF is very small component, and therefore most of the practical purposes and for approximate calculation purposes, RS and RF are considered to be 0. Okay. Whereas if we consider them in the circuit, then equivalent circuit during the positive half cycle, you will see there is a resistance RF, there is a resistance RS, and there is RL. Therefore, the current flowing through during the positive half cycle, say ILDC, is equal to the secondary voltage, say now denoted by say Vm, sine of omega t, divided by Rs plus Rf plus Rl. The peak value of the current is given by Vm divided by Rs plus Rf plus Rl. This is a Kirchhoff's voltage equation. Let us see what will happen during the negative half cycle. During negative half cycle, the input is changing the polarity. Therefore, voltage VAB also reproduce the same negative half cycle. When A is negative with respect to B, the diode anode is negative with respect to cathode, and therefore diode will be turned off. It is as good as acting as an open circuit switch, and therefore load resistance RL is disconnected from the secondary winding, and therefore voltage across the load is 0 during negative half cycle. And therefore, if we review back the positive and negative half cycle operation in this half wave rectifier, the rectified output voltage is available during positive half cycle only, and during negative half cycle the output is 0. And this repeats for all the input cycles. And therefore, we conclude that this rectifier can rectifies only half of the input cycles, and therefore it's named as half wave rectifier. Now let us see the same operation and the waveform at various points in the rectifier. Say right side figure shows the operation during positive half cycle. When input is going positive here, VAB, the diode goes in forward bias and current flows. So see here in the waveform, the first waveform is the waveform of the secondary voltage VAB with the peak value Vm. In positive half cycle, say 0 to pi, our diode D goes in forward bias and therefore start conducting, and it connects therefore the voltage VAB across the load. Therefore, if you see the waveform here, load voltage waveform, you will see same cycle is repeated from 0 to pi across the load. The peak value here is shown Vm, which is same as the peak value of the secondary voltage. Ideally, practically, the load voltage peak value will be less than the secondary peak value by the forward voltage drop across the diode, that is around 0.7 volt. If we know the peak value of the voltage across the load, the peak value of the current through the load is given by Im is equal to Vm by RL. If we consider the resistance of the secondary winding and forward resistance of the diode, then peak current value is given by Vm divided by Rs plus Rf plus RL. And therefore, the wave shape of the load current is same as the wave shape of the load voltage. Now, if you see the second half from pi to 2 pi of the secondary voltage, VAB is negative, and therefore diode will be in reverse bias, and it acts as open circuit, and therefore there is no voltage across the load, therefore VO is 0. So during negative half cycle from pi to 2 pi, load voltage as well as load current will be 0. Let us see the voltage across the diode. During positive half cycle, that is the interval 0 to pi. Since diode conducts, the voltage drop across the diode will be 0, ideally. But practically, there is a forward voltage drop of the diode, that is zero point 0.7 volt. During negative half cycle of the input, that is secondary voltage VAB from pi to 2 pi, since diode is reverse bias, the complete voltage VBA will be appearing across the diode, and that is the entire negative half cycle. The maximum voltage that is appearing across the reverse bias diode during this interval is minus Vm, and therefore, while selecting the diode for this application, we should be careful to choose the reverse breakdown voltage of the diode should be greater than Vm. That is also called as peak inverse voltage of the diode. Let us study the negative half wave rectifier. The only difference in positive and negative half wave rectifier is the polarity of the diode. If the diode polarity is reversed, the output voltage will be negative and the operation remains the same and similar like positive half wave rectifier. The half wave rectifier is evaluated by deriving various circuit parameters. Some of the parameters are listed here. First is the average DC load current denoted by ILDC. The second one is the average DC load voltage VLDC. Third one is the RMS load current ILRMS. Fourth one is the RMS load voltage VLRMS. Fifth is the ripple factor. If we know first four parameter, then ripple factor is just a definition in terms of first four parameters. And we substitute the derived equation from 1 to 4 points to get the ripple factor equation. Sixth parameter is a voltage regulation. Voltage regulation is the term which indicates the quality of the rectifier, how it discriminates against the variation in the input voltage and the load current. Means how good it is to regulate the output voltage to the constant value. The seventh parameter is the rectification efficiency. And the eighth parameter is the transformer utilization factor in this circuit. Now let us evaluate these parameters. The first parameter is average load current ILDC. Here for the sake of simplicity, I have reproduced the load current waveform. The load current flows from the half cycle 0 to pi, and from pi to 2 pi it is 0. Now, if we want to find out the average value of this waveform, we can apply the average value formula here. Average value IAV is given by 1 by 2 pi 0 to pi Im sin of omega t d omega t. It is also denoted by ILDC. Now, Im is constant, so we have taken it out. And sin of omega t is minus cos of omega t from 0 to pi. Substitute the limits. We will get here ILDC is equal to minus Im by 2 pi cos of pi minus cos of 0. The bracket term is minus 2 and therefore we will evaluate it to Im by pi, and therefore ILDC is equal to Im by pi, where Im is equal to Vm divided by Rs plus Rf plus RL. And since RS plus RF is much less than RL. Therefore, IM is approximately coming out to be VM by RL. If the values are given for RS and RF, then we will consider the complete equation IM is equal to VM upon RS plus RF plus RS for evaluation of value of IM. Now let us find out the average load voltage denoted by VLDC. VLDC is equal to ILDC into RL. It's a Ohm's law. Let us substitute the value of ILDC as we have derived it in step 1. That is Im by pi. So it is Im by pi into RL. That is equal to VLDC. Substitute the value of Im here, Vm divided by Rs plus Rf plus RL. Normally, Rs and Rf is much less than RL, and therefore VLDC is approximately coming out to be Vm by pi. We can derive the same expression by our common average value formula also. VLDC is equal to 1 by 2 pi 0 to 2 pi Vm sin of omega t d omega t. Whereas the signal Vm sin of omega t present at the output of half wave rectifier is present only from interval 0 to pi, and from pi to 2 pi it is 0. Therefore, we have written the formula VLDC is equal to 1 by 2 pi 0 to pi Vm sin of omega t d omega t. If we solve this integral, we are getting the average DC value Vm by pi, which we have already estimated here from Ohm's law using ILDC value derived in step 1. Now, we will estimate the AC and RMS load voltages and load currents. The RMS value of the load current is denoted by ILRMS. The name itself indicates it is a RMS value. It is a root mean square value. Therefore, we will take a square of the signal first, that is Im square sine square omega t d omega t, and find the average value of it. The average value of this current signal is 1 by 2 pi 0 to pi Im square sine square omega t d omega t, and therefore RMS value will be under radical sign 1 by 2 pi 0 to pi Im square sine square omega t by definition. Now Im square is constant, so taken out of the integral sign. Integral of sine square omega t is 1 minus cos of 2 omega t by 2. Solve the integral. We will get here Im square by 4 pi in bracket omega t minus sine of 2 omega t by 2 with the limit 0 to pi under the radical sign. Put the limits here and we will find that sine of 2 pi is 0, and therefore ultimately this equation reduced to under radical sign Im square by 4 pi into pi, and therefore that reduced to Im by 2, and therefore ILRMS, the RMS value of the load current, is coming out to be Im by 2. The RMS load voltage VLRMS can be obtained from the RMS value of the load current by using Ohm's law. So therefore VLRMS is given by ILRMS into RL. Substitute the value of ILRMS, that is Im by 2 here, and we will get VLRMS equal to Im by 2 into RL. Substitute the value of Im, that is Vm upon Rs plus Rf plus RL. Since Rs and Rf is much less than RL, this equation right hand side will be reduced to VLRMS approximately equal to Vm by 2. Now the next parameter we will see the ripple factor. The ripple factor is denoted by a small character r, and it is defined as the RMS value of the AC component at the output of the rectifier divided by the DC or average value of the output. The RMS value of the AC component is given by under root VL RMS square minus VL DC square, and the average DC value is given by VLDC, and therefore RMS value is given by this expression. Substitute the value of VL RMS as Vm by 2 and VLDC as Vm by pi and simplify. We are getting the ripple factor as 1.21 or 121%. The meaning is that this rectifier provides the ripple at the output which is 121% of the DC value, which is more than the DC value itself. So therefore, we can say that this is the rectifier which is not so good because it is providing lot of AC component at the output, and we are interested in the DC component of the output for our AC to DC power supplies. Next, we will evaluate the rectification efficiency. The rectification efficiency is basically a ratio of output DC power to AC power supplied to the rectifier, and therefore we first need to calculate the DC output power, that is PLDC. In terms of load current, we can write PLDC is equal to ILDC square into RL. Substitute the value of ILDC here as Im by pi. So therefore DC power output is given by Im by pi square into RL. Similarly, the AC input power is denoted by PAC, that is supplied to half wave rectifier from the secondary winding of the transformer. The PAC is given by RMS current IS RMS square into RS plus RF plus RL. This secondary winding supplies three components. One, the power supplied to the source resistance and the forward resistance of the diode, and the output power across the load. In practice, since RS and RF is very low, therefore power loss across this component is very small, and therefore it is approximately equal to IS RMS square into RL, and therefore we substitute here the value of IS RMS as Im by 2, since same current is flowing from the secondary during the positive half cycle. Therefore, AC power PAC is given by approximately Im by 2 square into RL. The rectification efficiency or power conversion efficiency is now defined as eta equal to DC power output upon AC power input, PLDC upon PAC. Substituting the equations of PLDC and PAC, we are getting the efficiency of 0.4 or 40%. It means that this rectifier is providing only 40% of DC power at the output, and remaining 60% of the supplied power will be lost, and therefore conversion efficiency of this rectifier is poor. When power handling required is very high, then such rectifiers are not suitable. The transformer utilization factor is the next parameter, and it is denoted by TUF. The transformer utilization factor TUF is defined as DC power output divided by volt ampere power rating of the secondary winding. That is equal to PLDC upon PSRMS. Whereas DC power output can be given by the expression we have derived for PLDC, or it is Vm by pi into Im by pi, average value of voltage into average value of the current at the output. Whereas the RMS AC power is given by the product of voltage and current at the secondary as RMS quantities. The RMS secondary voltage is Vm by root 2, but the RMS current flowing through the secondary winding is Im by 2 because it flows only in the half cycle. Solving this further, Vm Im from numerator and Vm Im from the denominator goes out. And therefore it comes out to be 2 root 2 by pi square, that is 28.6%. What it indicates? It indicates that the transformer device is utilized only around 29% and near about 71% it is remains idle. So therefore, we can conclude that transformer utilization is also not very good in half-wave rectifiers. The peak inverse voltage PIV of the diode is the next performance parameter. PIV should be greater than Vm as we have seen in the operation because it is the maximum reverse voltage appearing across the off-state diode. If this voltage exceeds, then the diode will go in avalanche breakdown and damage. And therefore, to avoid the damage of the rectifier diode, always while selecting the diode for rectifiers, the PIV rating should be satisfied. And here in this case, PIV rating of a diode should be more than Vm, the operating maximum reverse voltage in our circuit. The ripple frequency present at the output of the rectifier is same as the mains frequency. If the mains frequency is 50 Hz, then the ripple frequency of half wave rectifier is 50 Hz. Lower this frequency is, higher will be the size of filter required to eliminate it further. And therefore, half wave rectifier from performance parameter 5 to 11, we conclude that half wave rectifier is not very good rectifier for the purpose of AC to DC conversion. And therefore, in practice, normally half wave rectifiers are not used. In place of half wave rectifier, normally full wave bridge rectifier is used, which is having this performance parameter better than the half wave rectifier. So today we have seen the half wave rectifier circuit diagram, operation, waveforms at various points, and various performance measures, and we conclude about the quality of half wave rectifier. That's all for today. Bye bye.